We describe a system for high-speed acquisition of high-resolution dynamic geometry. Our system is able to obtain animated sequences such as these at 60 frames per second. We acquire data using a large lighting dome with 8 cameras and 1200 controllable light sources. The actor is illuminated with high-speed light patterns that are used both for tracking and to acquire normal maps. Slowing down, we see that each of the 8 cameras acquires images under several hemispherical lighting conditions, which we use to calculate normal maps. In addition, every fourth image is taken under spherical or uniform illumination and is used to compute optical flow vectors to compensate for motion. These are the normal maps computed from the 8 views, visualized as RGB. Because we use high-speed cameras and illumination, we obtain these normal maps at 60 frames per second. Our reconstruction process begins with the normal maps, as well as the visual whole computed from the silhouettes. We integrate each normal map to obtain a surface, with weak positional constraints and estimates of depth discontinuities provided by the visual whole. The integrated surfaces exhibit misalignment because of imperfections and biases in the data. Therefore, we perform matching on each pair of adjacent views, which tells us how to deform the scans to improve their alignment. We then merge the scans to obtain a single mesh and fill holes using constraints provided by the visual whole. A second pass of matching allows us to improve the alignment, and we remerge to obtain the final watertight mesh. We repeat this process independently for each frame. Our system does not perform any temporal smoothing. Here we show a dynamic reconstruction that would be difficult to reproduce with conventional stereo because of the lack of color texture. The partial surfaces can be completed with sophisticated geometry processing algorithms. For illustration purposes, we show the result of a naive method based on the visual whole. Because our system does not use a template, it can handle surfaces of arbitrary topology and overall shape. The detailed folds in the cloth and the lack of visible arms could not be reproduced by systems that rely on a human body template. The small-scale temporal flicker indicates that the reconstructed surface is close to the true surface. Applying some temporal regularization could further stabilize the surface motion.